this work is about computing controllers for contingent planning problems. So let's begin with an example of what is a contingent problem. So consider this navigation grid in which we have to go to position B and then go to A. That's the goal. Visiting B and then A. The thing is that initially we don't know where we are in that grid. And moreover, we have partial observability. So the only thing that we can observe is it is actually when we reach B and reach A. All right? So we can move to the right, to the left, and only we will see something when we are at B and at A. So we could solve this problem with a contingent plan, something looking like that. That plan is guaranteed to work for any initial state. So for example, if we are here, then 3 of these actions. So since in this position we don't observe B, so we are going to go to the right, and then to the right, and then to this guy. The 4th action is not going to apply. It's going to do nothing. And then we're going to apply 4 movement to the left, and then we're going to go to A. Right? So that plan actually solves that problem for every initial state. Is that right? Another possibility is to have like a program with loops, something like that, while not B do a right, and then while not A do a left. So when we reach the B, this while exits because we are getting the B, and then we start doing this guy, and then we hit the A. That program solves that problem. But there is a distinction here that this program not only solves this problem, but also solves like bigger instances of this problem. If we have like more positions, then the same program is going to solve that problem again. Whereas the previous plan only applies to this particular case. And also, if the actions somehow become non-deterministic, like for example, you do an action, a right action, and then with probability 0.9, you move to the right, and with probability 0.1, you stay in the same place, this plan is also going to work. So these kind of plans, they're very general. They're robust to changes in the domain. They're good. The thing is that it's very difficult to compute plans like that. What we deal with in this paper is controllers of that kind of that style. In this case, we have a controller with 2 internal states, and then we have transitions that are based on whatever we are observing, and then the action. Okay? So we can apply this controller to this problem. For example, starting at A, we always start at the initial state of the controller, so we are receiving the observation A, and the controller says go to the right and stay in the same internal state. So we go to the right, now we get nothing as an observation. We go to the right and we stay at Q0. We apply this thing, then we got to B. We get to B, then we receive the B, and in this case, we make a left and a transition to the Q1 state. Now we're in Q1, and then as long as we receive the nil observation, we keep going to the left. So that controller also solves the problem. It's pretty much like a plan with loops. So that is the kind of thing that we want to compute. So what are the advantages and disadvantages of the controller? Well, the advantages are they're compact, very compact. You can solve like complex problems with really real compact controllers. They are general and robust to changes like in the initial state, the dimension of the problem, and also in non-determinism of the actions. They are commonly used in robotics and games, but they have to be designed carefully, and this is often done only by human experts. So we like controllers, but it's really difficult to compute them. So the goals of the paper is that we want to design, we design an effective method for deriving these controllers, and the method is based in transformation between classes of planning problems, and then we use conformant and classical planners. So for the rest of the talk, I will tell you about the class of planning problems that we are dealing with. This is the class of contingent problems that we work with. The class of controllers that we synthesize, and then the technique is basically based in 2 reductions. One reduction from the problem of computing the controller to a conformant planning problem, And then a second reduction that in order to solve the conformal planning problem, that is from conformal planning to classical planning. Then I will finish with some more examples and then a conclusion. So we're dealing with partially observable deterministic control problems that are defined with a set of primitive fluent F, a set of clauses that define the possible initial states, a deterministic action that have conditional effects but no preconditions. We have a goal states defined in the standard way with literals. And the difference here is that we have a set of non-primitive fluents that are going to be defined with axiom rules. And among those, there are subsets that are called the observables. So let me give you another example. For example, we have this rectangular grid where there is an agent that initially doesn't know where it is, but the goal is to go to the the lower left corner of the grid. So we have a rectangular grid. The robot can move along the compass directions. There is a unknown initial position. The goal is to go to the lower left corner, and the agent at every moment observes the walls that surround itself. So we can encode that kind of problem with fluents like at x and at y that define the coordinates of the agent. The goal is to go to the cell defined or to the position at x0 and at y0. We have rules like conditional rules like this. If you apply the right and x is equal to 0, then x is going to be equal to 1, and then you delete the fact that x was equal to 0. And in this case, we have this set of derived fluents that are defined like with rules like that it says basically if you are in the top row, then you are watching a wall above you. And if you are in the first column, then there is a wall to the left of you. Right? It's clear? Everything clear? So we can there is a whole family of problems, continuous planning problems, that can be defined using this formalism. For the controllers, we consider what is called automata with output of the type Mealy machine. There are two types of automata with output. One is Moore machines, and the other one is Mealy machine. We're using Mealy machines. Mealy machines, you have automata, you have internal states, and then you have transitions that are labeled with the symbol in which you make the transition, and the output is that guy there. So in our case, a transition like that means that whenever you're in state Q and then you receive that observation, then you apply the action A and make a transition to state Q prime. So an automata can be characterized by a set of tuples of that form. And also, the consistency, there is a consistency property of these tuples that a controller cannot contain two tuples that being in the same state and receiving the same observation, that the tuples that you actually do contradictory things, like going to a different state or applying a different action. All right? So a given controller like that one can be characterized by a set of tuples. It's basically the same. This is basically the edges in the automata. And if the controller has only one state, we say that the controller is memoryless. When you have two states, there is some kind of thing that the controller has a bit that it can remember. Memoryless controllers are going to be depicted as tables. It's easier. Otherwise, you will have just one state and all those loops. So it's easier to depict a memoryless controller as a table. So this is the notion of solvability. A controller solves a problem P when every trajectory that begins an initial state reaches a goal state of the problem. So if that happens, then the controller is a good controller. It solves the problem. All right? So let's see an example. We have here the problem, and this is a memoryless policy. Observe here that you don't have the atomic observation of the domain. You have what is called the compound observations. So these are basically all the observations that you can receive at a given moment, right? So in this problem, I can actually depict the memoryless controller with this kind of diagram. For every cell, an arrow telling you what is the action to take. So it's clear that that policy solves the problem. So what is the computational challenge that we want to address is that how to obtain a controller of a given size. So I give you the problem, I give you the number of states, and then I would like to obtain a controller for the problem or an answer such as there is no controller of that size that solves the problem. Okay, for that, let me introduce the idea of interleaving. An interleaving is a sequence of tuples, the one that we saw, but in which the tuples are pairwise consistent. Okay? Every pair of tuples is consistent, meaning that they don't begin at the same internal state and observation and end up in an inconsistent output or state or action. So in the interleaving, it's a linear sequence. It's a sequence, so I can have the same tuple multiple times. Like here, for example, or here also. So an interleaving is just a sequence of tuples. All right? So let's define that an interleaving is valid for the problem P if and only if it solves P for every initial state. For example, we have this interleaving here, and let's consider our problem, and let's consider that particular initial state. So if I apply this interleaving, then this action here, or this transition here is not going to apply because I am not receiving that observation there. So the first tuple that applies is basically that one, is that you are receiving no observation, and then you make a down movement, and then that tuple there is not going to apply. The next one is that one that you are basically observing only a wall below you, and that one, and that will take that guy to the goal. So the same interleaving also solves the problem for that initial state. In this case, that tuple applies, the first one that to apply, the second one is that one, and then the third and the fourth. And then this guy goes to the goal position. Let's consider another initial state, that one here. So in this case, this fragment here of the interleaving is the one that is doing something. Right? So in this case, this interleaving here basically solves the problem for every initial state. Clear? So what we have here is a close connection between controller and interleaving. If I have a controller, I can generate an interleaving, and this is the thing, that if I have an interleaving that is valid for P, I can recover a controller from that interleaving. Every tuple is an edge of the graph. The interleaving tells me what are the edges of the graph. So what is the main intuition here? That interleaving is a linear sequence of things that solves a multiple initial state. Basically, that's a conformant plan. But it's a conformant plan that is working in a problem in which you have observations and the actions are conditional on those observations. So what we do is that we encode the observation of the problem at the propositional level, and then translate the actions also into conditional actions on those observations, so that the whole thing is translated into a conformant planning problem. And from a solution of that problem, if you can find one, then you can recover the controller. Or if the planning problem doesn't have a solution, it means that there is no controller of that size for that problem. Sure? Question? That's a parameter. The size, a controller, it is a parameter. You choose the parameter. I want a controller of one state or two states, and then with that number, I generate the conformant task. All right, so we have the mapping here from continuum to conformant. Basically, from a continuum planning problem like that, and an integer n, it's a parameter, we define the following conformant planning problem. The fluents are the same as the continuum planning problem, plus this This guy here that are the compound observations. These are possible observations that you can receive, the compound one. And we have a propositional symbol for every possible state of the controller. So Q is basically the end controller state. We have the initial state defined that way, basically saying that it could be any possible initial state of the contingent planning problem, but the initial state of the controller has to be Q0. The goal is the same, and then we have two types of actions. Action that correspond to the tuples that we saw, and an action, a special action that is the ramification action. That is the one that is going to take care of the observations. So basically what this reduction does is that it translates the compound observations and control state into fluents, sets the fluent Q0 to true in the initial situation and everything else to false. And let's see what it does with the actions. So whenever you have, for every tuple of that form, we have an action that is called BT. So first of all, we have conditional effects for making the transition in the controller. If we're in state Q and we are going to go to state Q prime, we basically do the thing at the propositional level. And then for every conditional effect of the action, we extend the conditions of that conditional effect with Q and O. So now all the actions become conditional on the current state of the controller and the observation that you're receiving. The ramification action, basically, we have to, first of all, define all the derived predicates. So for every axiom of that form, we have to include a conditional effect that takes care of the derived predicate or propositions. And then for every compound observation that is defined or that could be defined by that set of axioms, we need to add a conditional effect of that form. So here there is a potential problem that the worst case of that is exponential in the number of axiom rules, right? Because we have to consider all possible subsets of axioms. So, but there is still something missing from this. There's still something else to do. That the conformal planning problem is going to have this kind of actions and the ramification to the solution, right? If you find a conformal plan, it's going to have those actions. But we have to be sure that the actions are consistent between them. Namely, that the plan doesn't contain two BTs such that T and T prime are inconsistent. So let's define when a conformal plan is consistent or functional. We say that a conformal plan is functional if for every pair of actions, BT and BT prime that appear in the plan, T and T prime are consistent. So the formal result basically is that if pi is a functional conformal plan that solves Pn, then we can recover a controller for the problem. So the next reduction from conformal to classical is a known one. Basically, the only thing that we need to do is that we have to be careful about enforcing that the solutions are functional plans. So we basically modify the conformal planning a little bit before doing the translation, and then we apply the translation KS0 of Hector and Hector in order to obtain a classical problem whose solution such that we can recover a conformal planning problem from the solution of the classical problem. And then we can solve the resulting classical problem either with with any classical planner. We have used llama and also a SAT-based planner. So let me give you another example. Consider this problem here. We have a block word is in, and we have this marker here, and we want to position the marker on top of over a green block. So the thing that we can do is to move the marker down, up, left to the right, and then we have observations such as the block below the marker is not green, or whether the marker is at the bottom row of the scene, and whether it's something or not below the marker. This kind of representations is an indexical one, such as the one that you can find in the work of Chapman Ballard. So this is the controller. The nice thing about this controller, let me show you how it works. It basically goes like that. The nice thing about that controller is that it will work for every blocks where it's in. It doesn't matter how many blocks you have. It doesn't matter where, as long as the marker it begins at the leftmost cell. This controller here is going to find the green block. Another example is a gripper problem. You have to room the robot and 2 balls, and then in this case the gripper has a capacity of 2, and you have the observables such as whether there are balls remaining at the room B, whether you are holding something, and whether there is a space left in the gripper. So we were able to compute that controller here. That controller basically goes to the room with balls, picks up as many balls as it can, and then goes back to A, and then drops all the balls. And that controller actually solved the problem for every number of balls and for a gripper of an arbitrary capacity. All right? So to conclude, finite state controllers are powerful, compact, and robust, but they are typically designed by human experts. So we have shown that the task of computing such a controller can be reduced to the task of solving a conformal planning problem that is further reduced to a classical planning problem. And then we have used off-the-shelf planners in order to solve that thing to obtain interesting controllers. We have still scalability uses, like for example, sometimes the planner cannot cope with the classical plan, so there is something there that we don't understand. And also, if you look into the paper, there are more examples in the paper. That's it. Malta. Yes, I tell you something about that and something else. So there are 3 things, right? The first thing is, for example, you have a whole family of problems, and then you have a controller. So can we prove that the controller is going to work for that family? That's something that is not. We know how to do it for memoryless controller, but not for controllers in general. We are working on that now. But that's one thing. It's related to what we're saying. I'm going to go there. Second thing is that if you put a lot, if you overshoot the number of states inside the controller, you are going to overfit the controller, and then sometimes we were obtaining the class of controller that you're talking about. So it's not easy to. We don't know how to control the parameters of the problem that you need to solve in order to find the intended controller. I don't know if that is clear. And I promised you something else. Oh yeah, and the thing how to choose the right end. That's also something that is not clear.
So very much related with your first answer to some question. So in case of gripper, there is a memoryless controller that solves the whole family of gripper n. Doesn't matter how many balls you have. Gripper.
Yes, but that controller is more general actually.
Agree. But when you give this problem to a classical planner, you have to fix the number of balls, right? So how come you know that the controller that you end up with is general?
How do I?
You know it works for, suppose you gave your classical planner gripper problem with 10 balls. At the end, you know that your controller will work well for 10 balls. Maybe even you can prove that it works for less than 10 balls. So it's so clear for
How do I know that?
How do I know that it works for 11 automatically?
Okay, so the idea is to have some kind of homomorphism reduction, right? So if I have a controller for that guy, if suppose that we make it bigger, like, I don't know, one more row, one more column. So there is a homomorphic reduction from the bigger one to that one. So the middle cells are going to be mapped into the middle cell here, and the corners into the corners, and so actually this is not the smallest one for that.
You will have to find this homomorphism.
Yes, automatically. So the question is automatically. Yeah, I mean it's a work in progress. Yeah. So you want to ask a question or?
I'm going to answer the first question about yeah, but I think that I don't want to bother Derek.
So about the optimality of the controller, just remember when you have a code from a blank, then you extract the controller for them. But interleavings can be, long or short, and then translate to something that is more compact. So maybe even if you try to get short interleaving, they are not necessarily translated to controllers with less or more transition. But those things are really not correlated. Actually, I mean, we have, for the same problem, you can introduce, for example, additional uncertainty to try, just to see if you get something general. And for example, for some problems, you get symmetries, and for that particular case, you get a controller that does not generalize, and for other situations, you get one that does generalize. I mean, it's important progress, but it's actually no relation between short interleavings and compact or generalized